Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video, as you can see, is going to take a look at a lot of stuff. And this is basically Kip Irvine's book, Chapter 4, the second half of everything that you can find in there. So status flags, again, we're never, at least I'm not going to make you directly use the status flags in any of the programs. Some of the Irvine library does use that as return types and things like that, so we have to keep that in mind. But it also pays to keep in mind what the flags are, because again, indirectly, we're going to be using those for if statements and comparisons and all sorts of things in the future. And so you should know what these things do. So again, we're going to only deal with 4 of them. There are, if you remember from previous slideshows, there are 6 of them, technically 7. If you look into Chapter 9 when it comes to all the move operations that they have, all the string operations they have in there. So zero flag, sign flag, carry flag, overflow flag. So what happens is when you run any particular operation, like not including the move operation, all of the status flags get basically set or reset or cleared based on the result of the operation. So if I say like 5 minus 5, well, the 0 flag would be set because the result was a 0. It would be signed positive, so there would be a 0 in the sign flag. There wouldn't have been a carry or an overflow, so those would not be set. And so every operation does that, so you can check the results of every single operation on your CPU. And so we almost never do that, obviously, right? In C++, we don't even know that the status flags exist, let alone that we could actually go ahead and look into them and find out what's going on. So what happens is the contents of the destination operand is analyzed, and each of the flags are either cleared or set based on that result. So 0 flag. So, I mean, most of these are pretty obvious. The carry flags and the overflow is challenging sometimes, especially the one when we're dealing with signed values. How do we know if there's an overflow or an underflow? So the flag obviously gets set here when the result of an operation is 0. So if I, again, move operations don't modify anything. So, because it's just a copy operation. I mean, of course, it's successful. I copy data from point A to point B. So there's no reason, there's no actual mathematical operation going on, so nothing changes when it comes to the flags. So if I put 1 into the 16-bit CX register, and whatever was in there previously would still be there. And again, like, it all depends. I mean, it depends on what comes before it. But if I subtract 1 from that value, 1 minus 1 becomes 0. The 0 flag gets set. Very simple stuff. If I move FFFF into AX and I increment AX, of course, the 0 flag gets set because the result of -1 or max int plus 1 is equal to 0. And then also, if I take 0 and then I increment it again, the value might be 1, and then of course, because the result of that operation is non-zero, the 0 flag will not be set. So the sign flag is basically, we're dealing with signed arithmetic if we're staring at the sign flag. So this is one of those things you can completely ignore if you're dealing with unsigned values, because there's no reason to look at that most significant bit and go, hey, are you positive, or hey, are you negative, if it's an unsigned quantity. So, but anyway, there's a slide in here. Just understand, of course, to the CPU, the math is the math. The arithmetic is the arithmetic. So it makes no matter. It matters at nothing at all to it. If you have signed values or unsigned values, do it yourself. Figure it out yourself. Do some math and figure out that it's all the way you interpret the results that matters. It's just amazing how it all works out. So as you can imagine here, the sign flag, when we're dealing with signed values, the flag is clear, or 0 when the result is positive, or it's a 1 when it's basically a negative number. So all it's really doing is parroting and just mimicking and copying whatever the most significant bit of that quantity, of that register or variable is. So again, move 0 into CX doesn't change a thing. Subtract 1, FFFF, yep, that most significant bit is a 1, so yep, sign flag is set. Add 2 to bring me back to positive 1. Sign flag is 0. Decrement it, bring me back to 0. 0 is a positive number. In mathematics, we can always argue, is 0 positive or negative, but 0 in computer science is positive. And so then incrementing 1 more time to go back to 1 again brings the sign flag over to 0. So coming down, if I go ahead then and move 0 into AL, nothing changes. So the sign flag would still be 0 and all the other flags would still be whatever it is that they are. And so now subtracting 1 off from AL. Now this is all in binary. That's what, like, why are there 8 digits here? This is in hex, this is in binary. So now you look 1 1 1 1 1 1 because that's what we're doing, -1, right? And this bit is set, so the sign flag is 1. We add 2 to bring us again back to +1 binary. There should be a little b there, but that's okay. And then, well, I guess it doesn't matter which number system, 1 in almost every number system. And then you get yourself this 0, which extends out. That is the sign flag. That is the most significant bit. The result is a 0. Okay, so carry flag and overflow flag, these can get tricky. Thank goodness the CPU doesn't forget the rules, because it's all hardwired into that CPU there. So the carry flag is used for unsigned integers. The overflow flag is used for signed integers. My way of thinking and remembering it is that overflow is for signed, is like OS for operating system. I don't know. If you have a better one, good for you. I don't know. Like CUOS. I don't know. Just CUOS, something like that. Something stupid. So all CPU instructions operate here we go. Exactly the same whether we're dealing with signed or unsigned integers. It's just the representation and the interpretation of those results that matter. And so as a programmer, it's our responsibility to remember what we're dealing with, so that when we go to deal with what's staring at us, that we're able to interpret it correctly. So yes, the CPU does not distinguish between signed or unsigned math. And so that kind of, for multiplication and division, that kind of changes just a little bit, because of the fact that it's using completely different, it needs more registers, and it's a chapter 7 problem, something way in the future here, couple 3, maybe a month or 4 or 5 weeks in the future, 4 or 5 class sessions anyway. And so just understand that that is all occurring here. So the carry flag, and this is one of those things where it's just easier just to do than it is to explain. So it's unsigned integer math, carry flag, unsigned integer overflow. And again, when we're doing this in C++, we never get alerted. If a number comes out of the range and we overflow or underflow, we never see these things. We never see that. We just know that the result was borked. We don't know anything about it. So of course, it gets set when the result is too big or too small, either larger or smaller than the range of values that that number can represent. So this, like, how does an add operation affect the carry flag? The carry flag is a copy of the carry out of the most significant bit of the destination operand. And so that means that basically, it's complicated. It sounds real complicated there, but basically, when I do an operation, whatever, as I'm, adding, because everything's adding 8 bits or 16 or 32, whatever the most significant bit is, whatever the result of that addition is, or just the result of that operation pushing over into the carry flag, that carry flag is basically set from there. So like this, if this is -1 or max int, however you want to look at it, this is unsigned, so this is max int. So this is 255 staring right at us. And if I add 1 to this, I get 256. And when I get 256, I get 0. But in this consequence here, the consequence of this is when I get 256, zeros are what end up being the real number, but that 1 carries over, because 1 plus 1, 0 plus the 1 carry out of the most significant bit carries into the carry flag. And so the subtraction, remember, a subtraction operation is an invert, or it's basically addition of an inverted number or a 2's complement number. A minus B is the same as A plus negative B. And so remember that the CPU does that. So it's still an addition under the hood. And the reason why that is because then all the flags get affected the way they're supposed to be. Subtraction, I guess, would add more logic than is required. And I guess it's easier just to basically just pull a 2's complement on one of the values and do the math. So if I subtract 1 from 2, or 2 from 1, to get myself to a -1 value, it would get set, because 1 minus 2 is 1 plus -2. And the result, there's a lot of F's in there, or a lot of 1's in there. You can do the math yourself if you want to see -2 or 1 plus -2. You will end up with a negative number here, and you will end up with the carry flag being moved over. Okay, so for the carry flag here, so this is a little different than the 0 flag stuff we were doing earlier. there's so many details. I thought I was right in talking about the wrong stuff here, but increment and decrement operations do not affect the carry flag for whatever reason. Just so like if I have max int and I increment it, the carry flag does not get set accordingly. And so that's interesting, right? So just got to watch out for that if that matters to you. And applying the neg instruction to any non-zero operand always sets the carry flag. And the reason is, just think about it, we talked about earlier in a different lecture, that negating something is the same as subtracting from zero. And so it's subtracting from zero is the same as adding a negative number, or adding its negation. So in that case, because I'm starting from zero and I'm subtracting off essentially when I'm adding, the carry flag is going to be set as well. So here's a couple R turns. I'll just flip to the answers just to kind of get us going here. So we see, okay, so again, the move operation doesn't change any flags. And if I take FF as the whole quantity and I add 1 to this I guess is carry flag in all the flags here, and you go, oh my goodness, so I get 100 hex. Sign flag is 0 because it's a positive number. The 0 flag is not set because the result is not 0, and the carry flag didn't get set because we didn't overflow. Subtract 1 back, you get the same stuff. We're perfectly within the valid range of what a 16-bit number can represent. But now, interesting here, if I take 1 and I add it to just AL portion would be 0, 0, and the whole AX would actually be 0, 0, 0, 0 as well, because only AL is modified. And in this case, the carry gets pulled over because, again, the 1 doesn't go into the high portion of the AX register. The 1 goes into the carry flag. So the 0 flag is actually set because the AL register is 0, 0 in this case. The whole AX is, but the only thing we care about here is AL. So sign flag is 0 because it is positive. 0 is set because it is 0. Carry is set because we actually went from FF to 0, 0. We actually carried over into the 9th bit. Okay, so here's a little something. Here's 6C. Doesn't change whatever's in here previously. Let's take 95 hex and add it in. What do we get out of that? Oh goodness gracious, DEF 01. Okay, okay, I can see it here. 101 hex. It overflows, so it carries over, and the carry flag is set. And because it's not, it's a positive non-zero number, you can see why it's 0 and 0 here. Okay, so in full disclosure, I did modify the last one. Can I reach it? Right there. I changed that one. And that's because there was a typo in there, and I went into Visual Studio and I ran this and I proved that I was wrong. So I already did 7 minutes of the video, so I didn't want to change it. So just your PowerPoints will already have that in there if you're a student. Sorry about the change here. But anyway, so as you can see, remember that an increment here, so if I start with 2 and I subtract off 3, as we were saying, that you end up with the carry flag getting set because we underflowed or over, we went from basically a low number to a large number. But if we increment, that was just one of those rules. Increment and decrement does not modify the status of the carry flag, but it affects everything else. So the sign flag was set to 0, and the 0, because it's a positive number, the 0 flag is set because we're staring at 0, and the carry flag is the same. So it's a little confusing here, right? Because it's like it stayed the status, but if it was a 0, it would have stayed a 0, and we would have been really confused, right? So that's just a forewarning. I don't know why increment doesn't affect the carry flags, and at this moment in time, I do not have the means to go, and I got to get these videos done to find out exactly why. So the overflow flag is the same kind of deal, but it's used for signed integers. So like again, if carry is what we use for unsigned, overflow is what we used for signed integers. So it's the same overflow, underflow, that kind of stuff. When the signed result is invalid or out of range, then the thing will get set. And it's a bit more confusing to deduce because it's an XOR operation, and it's all sorts of weird because instead of moving a digit over into a carry flag, we're dealing with the fact that we're already dealing with a bit inside of the number itself. So I'm taking, like, notice with this 0, 1, 1, 1, 1, 1. This is positive 127. And then if I add 1 to it, it turns into 100000000, which is negative 128 if you're dealing with signed numbers. So yeah, you better believe that even though there's no carry, I didn't carry off into the 9th bit, but I turned a positive number into a negative one. And that's not supposed to happen. True mathematics would never allow that, right? 127 plus 1 in true mathematics would be positive 128. But instead, because we're dealing with a silicon chip and we're doing the best we can, we end up with negative 128. So the technical term for this is the copy of the carry flag XORed with the most significant bit of the destination operand. Just let the CPU handle it, right? And let's see, the overflow flag for subtraction is the copy of the carry flag XORed with the most significant bit of the destination operand. So it's the same thing as the add operation. Whoop-de-doo, right? So again, let's just talk about the rules. Don't worry about the specifics. If you're going to go into computer engineering, yeah, worry about it then. But for the most part, that's why the flags are maintained automatically for us. So the overflow flag is used for signed integers. Some things to consider: whenever you add a positive number and a positive number together and you get a negative, the overflow flag gets set. Makes sense? When you add two negative numbers together and you end up with a positive number, it's the same deal. There you go. And so, but what happens is just kind of look at the math, kind of if you want to look at the ranges for the values that any register or any variable can have. And if you add any positive number and any negative number together, when it comes to this in the same bit size, you can never overflow. It's just impossible. So it's one of those things. So the only time this could ever happen is if both operands are the same size. So just keep that in mind. And so one more your turn here for the overflow flag. So let's take a look. Remember, all the move operations don't change any of the flags. So that's all good there. This is already the most interesting one. I guess I'm going to give away the secret here. Negative 128, 10000000. What would happen if I want to negate that? So flip all the bits and add 1. And what do you end up with? You actually end up with 10000000. The negative 128 is equal to negative 128. Put it into Visual Studio and C++. Find out. It absolutely is true. The negative max int or the min int or however you want to look at it is the one value that cannot be negated correctly. Every other value in the range can be negated correctly, and that's because the range of values for this is negative 128 to positive 127. So every other number has a match on the number line on the other side, the negation of it, but 128 doesn't. Negative 128 does not, or positive 128. Okay, so if I take 8,000 hex and add 2, obviously 8,002 hex didn't do anything to carry or overflow. Oh, coming back. Yeah, notice this one affects carry and overflow because this is basically screaming out that we didn't even get the correct math operation. Yeah, because not only is there carry overflow, but it's not even the right value even if we tried to mod it, because it should be negative 129, or it should be like something like, I don't even know what it's been a long weekend. What would that number be? 10000001. What would that number be? Negative 127 or something like that, or negative 129. Whatever. Let's just move on. Okay, so if I take 0, I subtract 2 off. Again, the carry flag gets set, but the overflow doesn't necessarily get set, because going from 0 to negative 2, that's perfectly legitimate inside of the range of the 16-bit integer. And so again here, the overflow flag would get set. Negative 5 subtract 125. Negative 5 minus 1 plus negative 125 gets me negative 130. It's not in the range. There was an overflow. So again, this confuses everybody. You don't have to think it out every time. You can see me kind of hemming and hawing through a couple of these. So it is challenging. So spend a little time and think out what's going on as you're doing your stuff here. Okay, so let's move my body over here just a little bit. And now we're ready to talk about specifically a little bit more about the assembly language of these kind of operators that we're going to need for the rest of the term. So in assembly language here, whenever I see the keyword offset, the offset operator, I know I'm dealing with a pointer to a variable, or it's basically a pointer to a memory address, and most likely, if not always, it's stored in the data segment. So, and I guess it is always in the data segment. Returns the distance in bytes of a variable from the beginning of the data segment. You don't have to worry about that necessary detail. You just have to know, like in this case here, if I have these different data types all set up, bytes and words and double words and so forth, excuse me, so that if I say, okay, give me the offset of A, and, if I didn't have offset in here, we would move 1 into ESI. But because we're saying offset, we're taking one extra step and saying, okay, not only, I don't want the value of what's stored in A, I want to know the actual memory location in RAM for where this thing is stored. And so that's going to come out, and it's the reason why it comes out as this value is because that's the first byte in this array. And you can see everything is jam-packed in here as close as possible. Here's my A, here's my B, here's my C, 4 bytes, D 4 bytes, E 1 byte. So you can kind of see how things work out here. And again, this is all automatic. We don't have to worry about the numbers, just like when we're dealing with pointers and references in other languages. We almost never care what the actual value is of the pointer or the reference. We just care that we have it so we can do stuff with the data stored at that memory location. So if I say offset A, it'll put in a pointer. And so you always have to use, because of the environment we're working in, you always have to use a 32-bit value, because offset stands for pointer, memory address mode in our system, right, for this course is 32-bit. So it always needs to be, if you're going to store it as a variable, I think we'll show that in the next slide, it has to be a double word. And this is a double word sized register. So offset of A goes into ESI, offset B, C, D, and you can see again what memory address goes. So, okay, so here's another example. Let's compare C++ versus assembly language. So, okay, let's see. As you may have noticed, the operator basically will get a raw 32-bit pointer, there you go, raw meaning untyped. Where, in C++ we have an int pointer or a character pointer. Basically what we get here in assembly language is what we would call a void pointer. We have a raw memory address, and technically we don't know what it is. We don't know if it's an int or a byte. I mean, we do as programmers, but the compiler, the assembler, has no idea. Just has no clue, because it's just a raw pointer. So here we say, I want to set up a 10-element array, character A, and I want to set up a pointer to that. Okay, so this is how we would go about doing it. This is not exactly the same. I'm not setting up a p variable here, but this is how you would go about doing it. I would set up signed byte, these are signed characters, signed byte 10 duplication question mark, uninitialized data. I call it A. Give me the offset of this thing. Give me the pointer to the first element in my contiguous block of memory, and put it into ESI. And again, I make sure, because the offset gives me a 32-bit quantity, that address is a 32-bit quantity, I have to put it into a 32-bit register or variable. So all of this is uninitialized. And again, I'm pretty sure, I'd say every time I run the programs in assembly language, this is the actual start value, because they're all offsets, and they're all, the program is put in different places in memory when the operating system runs the program, but it's all a matter of offsets from different positions. So generally speaking, this is seems to be always the value that comes out of the deal here. Okay, so here's a tricky one now. And this just comes down to the fact that, again, that assembly language doesn't know, when it's looking at a memory address, it truly doesn't know what it's looking at. And a lot of times you have to kind of, you as the programmer, because you know better, have to tell the assembler what's going on with the pointers. Tell it, oh, treat this like a word, treat this like a byte, treat this like a double word. And so, and this is where things get, oh my goodness, this is where things get tricky too, because especially with variables and little endianness, and how if I'm using if I move a variable onto a register, I'm flip-flopping all of the endianness. And let's take a look at this example. Let me move my body over one more time here, and let's take a look at that. Okay, so A, D word, 1, 2, 3, 4, 5, 6, 7, 8. So in memory, in pure memory, remember little endian order, so it's actually 7, 8, 5, 6, 3, 4, 1, 2, byte for byte. Okay, let's just start there. And so now this is an error, of course, because this is double word 32 bits. AX is a 16-bit register, so I can't do that, just to say. Okay, so now here's the fun part. If I move A into the EAX register, that's legitimate because they're both 32 bits in size. What happens is the EAX register reverses the positions. So basically the register always will hold the values in big endian order, if you want to think of it that way. So now, so it flip-flops everything. So it's 1, 2, 3, 4, 5, 6, 7, 8. This is the EAX portion. This is the big giant EAX. And AX is actually storing 5, 6, 7, 8. You might think it's the reverse because of the way things are here, but remember, but the CPU does this all automatically. Okay, but now what gets interesting about this here is if I say, okay, because of the way A is stored, here I say take A, treat it like a word pointer, or treat it like a word, and put it into AX. Like up here, that was illegal a minute ago. I can't directly take whatever a pointer to A, and say take 4 bytes of storage or 2 bytes of storage and move it into the AX register because this is a double word. It's not allowed. Double word is too big. But this is basically an override, and this is saying, yeah, because a memory address is a memory address, a pointer is a pointer is a pointer, you're free to go ahead and just say, once you have a memory address, you're like, it's a double word, treat it like a word. And what will happen then, as you can see here, what it actually copies in, because of the way the memory is set up, we're not talking about the register here, we're going over here, it's going to move the 5, 6, 7, 8, because those are the 2 bytes that are closest. If I take A and I say treat it like a word, run that again. Like I said, this time around, I'm not mumbling that one. This is true stuff. If I'm treating A by itself here and taking A and treating it like a word, I'm taking these 2 bytes and moving that into the AX register. So 5, 6, 7, 8 is the value. So the same thing goes now. If I say, so nothing has changed in A here. A has never been modified until this line of code here, where I say, okay, A, okay, put 4321 hex, that's 16 bits, 4 characters, 4 bits per, right? So that's basic, 2 bytes of storage. Go to A, treat A like a word, and put those values in. And again, because of the endianness order, the 2-1 goes in the first byte, the 4-3 goes in the second, and the other 2 are left unchanged because we're only dealing with basically the 2 bytes that are the word portion, as if A was, if that's what A is, what we were dealing with. So if maybe you've heard of this, maybe you haven't. I've used reinterpret cast out in the field. Reinterpret cast is basically what is going on here, where as long as you have a pointer to a memory address, you are generally allowed to go ahead and say, treat it like something else. Take this byte, treat it like a word. Turn this werewolf pointer into just a pure character array. And so we actually do this kind of thing out in the world too when we're dealing with binary files. Because like if I have a pointer to a record that has like 32 bytes of storage or something, I'm like, I could just tell it just to spit out 32 bits. Or 32 bytes. I could just go ahead, treat it like a byte array and just spit it out. Because again, RAM is RAM is RAM. As long as you can get to a memory address, believe it or not, or as scary as it sounds, as long as you can get there and the operating system doesn't pitch a fit, you can do whatever you want with that memory address. Okay, so let's see, anything more here? Yep, so another example here of everything going on here. So, okay, so 1, 2, 3, 4, 5, 6, 7, 8 in memory. Again, reverse order because of the little endian order. So now what we can say here is take A, pointer to A, treat it like a byte, and put it into the AL register. So again, you might not believe it, but the 7, 8 would go in there. You would think the 1, 2, because of the way the bytes are stored, but because of the endianness order on our architecture, 7, 8 goes in. And so A plus 1, right? Like take A, move 1 byte over, treat that like a byte, and put it into AL. That's where you get the 5, 6. Okay? Same goes for this one. Go to A pointer, move over 2 bytes, treat it like a byte, and put the value into AL, 3, 4. And so now this is where things get more interesting, of course. So now A, treat it like a word. So these 2 bytes here, treat it like a word, and then move that into AX. And again, because of the way things get flip-flopped on the register, 5, 6, 7, 8 is what is stored. And so then one more time, go to A, go 2 bytes over. You might get a little confused because you see 2 and you see word, but it's always, the plus is always in bytes. Always, always, always in bytes. Take A, go over 2, treat this like a word, and put that into AX, and that's why it comes out 1, 2, 3, 4 again. And so again, this is so confusing for a lot of people, me included. Only in the last year or so, it became a little more second nature, especially explaining, because it just melts your mind. Because if you go from RAM to a register, it reverses everything, and then when you go from the register back to RAM, it reverses it re-reverses it back a second time. And so again, as long as you're not dealing with memory on a byte for byte basis like we're doing in this example, you really never have to worry about this kind of stuff. I mean, but it is, every so often, we do have to go into memory 1 byte at a time for things that are larger, for data types that are larger than 1 byte. And when we do that, we have to take into account that our little endian system is going to have some of these bytes reversed on us. Again, memory is memory is memory. Pointers are pointers are pointers. So this pointer operator can be used to combine elements of smaller data types to move them into something a little bigger. So like, and again, let's say I don't have to remind you after talking about this over and over and over again, the CPU will automatically reverse the bytes. Okay, so this is a little different than before. Notice this is a byte array as opposed to like a double word, right? This is a double word, 1, 2, 3, 4, 5, 6, 7, 8. That's why everything's in reverse order. But in this case, since I'm specifying a byte array, I'm specifying every byte along the way. No element is larger than 1 byte. So this is essentially how you would put this value into big endian order into the memory location wherever A is stored. And so remember now, okay, if I take A and I dereference it, so just A, if you want to think of A plus 0 or A0 in square brackets, whatever you want, go here, treat it like a word, and put it into AX. So 3, 4, 1, 2. Everything again reverses. So 3, 4, 1, 2, and this is left question mark because whatever was in AX before is still in there. Okay. So again, it's 1, 2, 3, 4, right? Oh boy, right? However, it's that's just the way it reverses here. So now if I go to A plus 2 and do the same thing, 5, 6, 7, 8 will go into the register, but essentially it's 7, 8, 5, 6 that's stored there. So the final example then, if I take A, which is a 4-byte array, and again, pointers are pointers, memory addresses are memory addresses. As long as the operating system doesn't pitch a fit, I can do what I want. So actually, since this is a byte array, I can say, hey, go to A, the first byte, treat it like a double word. Just treat this thing like it's 4 bytes of storage. And of course, you have to, as the programmer, have to make sure you can actually access 4 bytes of storage. And so I go ahead and I say, take A, treat it like a double word, and move it into EAX. That's no problem. And again, it just gets reverse order. 7, 8, 5, 6, 3, 4, 1, 2 gets put into the EAX register. So the only thing throwing us off here is the fact that we're in big endian order, moving everything in reverse order and back and so forth and so on. So again, this is a big source of confusion for a lot of students and a lot of teachers, and especially when they first start teaching this stuff. But so please take a little bit of time to understand what's going on, and just understand. I'll just say real quick, everything would be completely different if we were in a big endian system, but we're not. So we have to deal with what we have to deal with here. Okay, oh, I guess we have another example. Okay, one more time here. So let's take a look. So let's see. Again, remember the little endian architecture here. So let's just go to the answers and see what's going on. So, okay, this is the byte order. Put a 6, 5, because these are bytes, comma, 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 6, 5, 3, 1, 0, 2, 0, 5. And then I have 6, 5, 4, 3. Remember, these go in reverse order because of the way these are larger than 1 byte. So 4, 3, 6, 5. 0, 2, 1, 2, and then this one completely in reverse order, 7, 8, 5, 6, 3, 4, 1, 2. And so this is how all the bytes would be stored in RAM. This is how you would access them if they were all normal arrays. And so now what do we do here? We say, okay, go to A, this byte here, go over 2, treat this like a word and move it into AX. So that's why you can see now these 2 bytes here, 05, 02 in reverse order, okay? Go to C, which is a double word, but treat it like a byte and put it into BL. So this byte is 7, 8. There you go. Take B, the start of B. Now this is where things get tricky, right? You like B2. There's no B2 with bytes. Right? All of this is bytes, right? Again, not elements, bytes. So I go to B, I say, okay, B, go two bytes over, treat it like a byte, and put it into BL, 0, 2 goes in there. Okay? Take C, go over 2, treat it like a word, and put it into AX, 1, 2, 3, 4. Fair enough. Take B, which is 2 separate words, but treat it like a double word, and put that into RAM, and you get 1, 2, I'm sorry, put that into a register, you get 1, 2, 0, 2, 6, 5, 4, 3. Oh, goodness. Hopefully we're done with this, right? I keep saying that this is the last example. Okay, fine. Moving on. Different languages, different terms for things. So the type operator is basically a SIZEOF operator, which confuses things because there's a SIZEOF operator in assembly language. So as you can see here, if I do type A, what'll happen is the assembler will go, oh, hey, A, and it'll work its way back and go, A is a byte, so it will fill in a 1. And it literally will fill in a 1 into the EAX register. What's nice about this is you don't have to hard code things, because maybe along the line you change a byte into a word or a word into a double word or whatever, right? There's at least 6 different combinations there. And what will happen is you don't have to rewrite any of your code. You don't have to remember to, because this will automatically update when you go and assemble again. So again, type A, that'll give me a 1. Type B will give me a 2. Type C will give me a 4. Gotta make sure I say the right things. Type D will give me an 8, because it's just a matter of how many bytes does that data structure make up. And so length of is a little different then. Length of returns the number of elements in an array or variable. So you can kind of think of a variable as an array of 1. Does that help anything? Just think of it that way. So like in this case, well, I guess it's not here in this case, or in these cases, but just a simple variable, the length of would be 1. Because it's only one variable. It's only, we don't have a list of them, it's only 1. So in this case, look at all this kind of stuff here. Length of A, you can go 1, 2, 3 elements. Length of B, 30 duplicates of uninitialized data, then 2 zeros afterwards, 32 of them. This is weird. 5 duplicates of 3 duplicates. This is actually like a multiplication. This is a product. 5 times 3 gets me 15. And why wouldn't you, this is just to show different things. Normally, I guess you'd say 15 duplicate question mark, but whatever. 1, 2, 3. It doesn't matter the data types. So 1, 2, 3, 3 elements. And in this case, this can be a little tricky. You might think this is 2 elements. Here's 1, 2, 3, 4, 5, 6, 7, 8, and a 0. But since these are all byte elements, there's actually 9. There's 9 sizes. There's 9 index values available to me. Okay, so here's that SIZEOF I was talking about, and essentially SIZEOF is type times length of. It's basically how many bytes does the entire data structure consist of. So it's just basically number of elements times its size. So 3 times 1 is 3, 32 times 2 is 64, 5 times 3 times 2 is 30, 1 plus 2, 3 times 4 is 12, and then 9 times 1 gets me down to 9. Okay, so let's take a look. So now, as we were trying to do earlier about direct and indirect operands, there are many different ways we can access the arrays, and this is just one of them. So let's take another one of them. Let's take a look now. Okay, so this is called indirect because it's different than how we were doing things before. The way we were doing things before, we were essentially doing things the way we would do them in C++ or Java. We would say, hey, A, go to the 5th byte or go to the 7th byte or something. We would put that number in square brackets. And notice this is not the same kind of thing. We're using the raw pointers instead of memory addresses and offsets. So here, let's see, what am I doing? I'm just incrementing, just changing stuff around and just getting information. So so let's take a look. So here's a 3-byte array. And so I can say, okay, get me the pointer to A, so that it'll get me the memory address of where the 10 is stored here, and it puts that into ESI. So now I have basically, I basically have a pointer to A. And so what I can do is I can say dereference that memory address. And so now that I'm pointing there, I go, okay, I'm dereferencing it, and I'm going to put the 10H into the AL register, because that's what the square brackets essentially indicates, is that you're dereferencing something. And then now, here's the big deal here. Notice I do increment ESI. Notice it's not square bracket ESI. It's ESI by itself. So here, notice the difference between the two. ESI, without the square brackets, manipulates the value stored in the register, which is the memory address, which means by incrementing ESI, I'm taking my pointer, which is pointing to 10, I'm moving over 1 byte, and now I'm essentially pointing to the 21 in memory, as opposed to square bracket ESI, which is the dereference operation, which says, okay, I'm presuming that whatever ESI is a memory address. Go there and get me the information stored there. Huge difference. So that's why after I increment and I say, okay, get me dereference and put the value there, that's why the 21 comes about, because I've moved over to here, and now when I go and dereference that, I'm getting that value. And that's why when I increment another time, I'm into here, and when I do this one more time to move square bracket ESI, the 32 comes for the ride, and AL now holds the 32 value. Things can get tricky when you do this, though, because again, the raw pointers are pointers, but to assembly language, we're dealing with raw pointers, and sometimes the assembler can't figure out what to do. So this is one of those examples. So you have to use the pointer operator, which we discussed previously, to clarify. So I have a word variable called a, initialized to 0. It's pretty much irrelevant what it's set to. But if I say, okay, get me the pointer, put it in ESI. And again, all pointers have to be stored in somehow in 32 bits of storage. But now you notice I put inc ESI, which feels like it's perfectly legitimate. I mean, it is. I mean, it truly is a legitimate thing. But the problem is it's ambiguous, because all we know is, all the assembler knows is that ESI is storing a memory address. It does not know, like C++ or Java, if it's an int or a character or a who knows what. And so we have to supply that information because we know better what's going on, so the assembler doesn't have to guess. Because the assembler is never going to guess. Because if it guesses wrong, your program is going to go, oh my goodness, go all belly up. And so we have to do it ourselves. So now we can say, okay, I know ESI is a pointer to this guy here, but treat it like a word. And earlier we were kind of ruining everything by treating words like double words and all sorts of crazy nonsense. But this gets the point across where it's like, okay, ESI is a word. Let's treat it like a word so that we actually get the information like we're supposed to. The 0 that's stored there, A would be incremented to 1. So A is actually incremented to 1 after this is all said and done. So let's do this with another example here. Same deal goes. Same stuff. It starts out the exact same. A is a word. I'm incrementing just ESI. And it doesn't matter if it was a word, a byte, or a double word, whatever. It doesn't matter what the data type would be. This will always be an error because it's always ambiguous what ESI is actually pointing to. So cross that out. And again, we fix it up with inc word pointer ESI, which means that A is now incremented to 1 correctly. So I can now say, okay, go to that memory location, which is ESI, and move it into AL. And now this is, it's like the tricky part here is, if this was ambiguous, why isn't this one? And the reason is this has context. This had no other context to go off of. But this does, because AL tells me that's an 8-bit register. And so that tells me there's context to say, treat this like a byte pointer. And so you can do that. Like if I wanted to, you could put byte pointer ESI, but because, and it'll be perfectly fine, but that's essentially what you're getting without putting the extra verbiage in there. Because in this case, I can refer to here to figure out that it's supposed to be 8 bits. And so remember now, if A is 1 sitting in memory, in little endian order, the first byte is 1 and the second byte is 0. So it's reversed. That's why when I increment and I increment everything out here and I print it out, or I move it to the AL register will hold the 1. And then if I say, oh, hey, ESI, pointing to the first byte of A, move to the second byte of A, and then move your contents into AL, that's why the 0 comes next, because of the little endian order. Do this on a big endian system, the bytes will be reversed. 0 will come first, then the 1. Okay, so more examples here. Oh goodness me, oh my, right? So again, Java moves everything, C++ moves everything one element at a time because it knows what the elements are. Assembly can only move bytes at a time because we don't know what the elements are, and byte is the only, basically byte is the only common ground we have between all the different data structures. Okay, so let's see, a program that sums up everything here. So go to the offset of A, get me that, and put it into ESI. Okay, so the pointer to the first element is stored there. Dereference it and put it into AX. I don't need word pointer here because AX is already a word sized element, so 1000 hex gets put in there. But notice now, I can't move over, I can't add by 1, I can't increment because this is a word array. And so I have to take the ESI pointer and move 2 over to get from here to here. And then it's the same deal. Then I can dereference ESI and add that to whatever was previously stored in AX. So AX will store 3000 hex. And then notice now, talking about that type operator, instead of hard coding the 2 in there, I can use type A, which will fill in the 2 automatically for us. And this is the better way to go. It's a little more complicated, requires a little more thought process on it, but you can see that it's definitely more flexible in the long run. So this will move over to 2 bytes anyway to 3000 hex, and when I add that in, I get 6000 hex as the end result. And now I'm ready to do whatever I need to do with the AX register. So then the same thing goes for double word, just larger elements and different sizes. So if I move, but again, the pointer is a pointer is a pointer. It's always going to be 32 bits. So offset of A goes into ESI. Dereference it as a double word, because it's an EAX register that's getting copied into. So it knows to take this whole thing and put 1 million hex or whatever in there. Add 4 to ESI because I got to go from this byte to this byte to be able to move one element over. And then do the same stuff as the previous slide. This will add 2 million hex to get 3 million hex. And then now type A works the same way to say move 4 bytes over because we're dealing with a double word array inside of there. And so then adding the ESI one more time brings everything up to 60 or 6 million hex. All right, so now, again, coming back to the way C++ works out, these are the basic 2 different ways we could go and access the elements in an array. I've already shown this in a previous video where you notice that this is A plus ESI, everything in square brackets. You can also reference it like this, A with ESI in square brackets, and this is the more common way of doing things when it comes to how most programmers operate in almost every single language. But again, C++ has this fancy way of having a second way to reference this, and a lot of times actually this is a faster, more efficient way. Somehow the compiler produces faster code when you use the more complicated syntax for this thing. So let's take a look at this, how these 2 methods work out. Whatever works for you is perfectly fine for this course, obviously, until if there's ever a problem. Sometimes I get issues trying to figure out, and like with this, sometimes one of these doesn't work, and sometimes one does. So I just use whatever one works. I don't know why that problem. Next time I encounter it, I'll have to look into it a little more. But okay, let's see. Move 0 into ESI. Okay, what is that meaning here? And now if I say A plus ESI, that's essentially saying A sub 0 or index 0, and take the A0 and put that into AX as a 16-bit quantity. So this is the first element. It's word size. 1000 goes into there. And so that's perfectly fine. Move 2 over, take ESI and move 2 over, and then now the alternate way of doing things is say, okay, A2 in square brackets, get me that value and add it into the AX register. So just like before, like the 3rd or 4th time we're doing this, 2000 hex gets added in, 3000 hex is our result. And the type A still works. And now, since it's a word array, it's going to add 2 again, but again, it's automatic. And then now back to the old way here, A plus ESI. This is A sub 4. Go there, 3000 hex, add it in, 6000 hex is your end result. Let's do it one more time. So double word again. So 0 goes into ESI. A sub 0 as a double word is 1 million hex. Put that into EX. Don't mind this, is just a slight typo. 1 million hex goes in here. Add 4 to move over 4 whole bytes to get me to the next element. Take that, A sub 4, and go there and add the 2 million hex to get 3 million hex. Go one more over, type A, 4 bytes, it's a double word, boom, over to here, add this. So again, whichever way you prefer, but the better way at least is to use type for this, and whichever way for this works for you. I like to use this personally, especially when we get to the like chapter 8 stuff. When it comes to using EBP and ESP and all sorts of stuff, I like this. But again, if it doesn't float your boat, I'm perfectly fine with you not worrying about it there. Okay, so pointers. I do have another video that explains references, pointers and regular variables. It's like a 14-minute video or something like that. So I highly recommend just kind of going through that at the same time. This is just a quick once-over when it comes to the way pointers work. So a pointer variable can be declared as a variable. We don't have to just put everything we've been doing up to now, we've just been putting it into a register. So we can do things either way here. And again, remember that on our architecture, a pointer is 32 bits of space, so it always has to sit in a double word. And so for whatever reason, this is B D word A and C D word offset A. These are exactly this, they end up being exactly the same. I prefer to put the word offset because that screams out pointer to me. This does not always scream out pointer, because a lot of times if this wasn't an array, it would just copy the value, right? So whatever. So C, D word, offset A. So B and C are all pointing. And now here's the fun of pointers, right? A is pointing to the array. B is pointing to the array. C is pointing to the array. So that means that the data is in one place in memory. All however many, let's see, word, 6 bytes of storage. It's only in one place in memory, and there's three different ways to access it. A, B, and C. So remember then, since they're pointers and the memory is only in one place, if I change it through any of those three means, it affects all three. Because it's not 3 copies of the data, it's 1 copy with 3 ways to get to it. Okay, so let's see. If I do move B into ESI, because B is already storing a pointer, so I don't have to dereference it or anything like that. I can go ahead and just say, okay, put B into ESI, dereference it to get me the AX, treat it like a word, so I get 1000 hex. 1000 hex goes into the AX register. And so I can also say C, give me C, which points here, go 2 bytes over, treat that like a word, and so that's an alternate way to get the 2000 hex. I could do C plus 2, I could do B plus 2, I could do A plus 2. I could do all 3 different ways to get me to that end result. In chapter 6, we'll talk about a whole ton of different jump operations, conditional jump operations, but this one is an unconditional jump. So, I mean, it's exactly what it sounds like. So there's no such thing as goto. Just repeat that. There is no such thing as goto in C++ or Java. And that's because we don't need it, because we have ifs and for loops and all sorts of crazy stuff. But assembly language, there's no way to get around it. There's no way to get around code, using the data structures of the assembly language. So we have to use unconditional jumps many times. And so what happens here is, this is a program that will infinitely print out the never-ending string. And so here is a label. So that's what a jump does. So a label is just basically a pointer to the next memory address, because that's how you know where to go to when you jump to it, jump to the label. So you say, okay, put the offset of A, the pointer to A, into EDX, and call write string. That's what that function requires. Give me a pointer, and I'll print out that thing until I hit a 0. So it prints it out, and then it jumps again. And so basically it unconditionally jumps up here and falls through, unconditionally jumps, falls through. So it's just an infinite repeating loop until you get tired of staring at that thing and you stop the program. And so that's all there is to it. So just, you have to be used to that, because we're going to start using this a little bit more and more, especially when we get into more complicated data structures. So now that ties differently here than the loop instruction. The loop instruction is a little more complicated. It still uses a label and it still jumps, but this is our first conditional jump statement, if you want to think of it. It's a loop. And so it's a counting loop. And unlike most loops we use in programming languages and high-level programming languages, we actually start counting down toward 0 as opposed to usually counting up from 0, right? Whenever we use a for loop, for I equals 1 to 10, do something. But in this case, we would start at 10 and work our way back. So what happens when a loop instruction is encountered? So now we get the first rule of like what registers are used by certain instructions. The ECX register is used by the loop instruction. You never see it, it's indirectly modified, but the first thing that happens when you hit loop is you basically decrement ECX. You subtract 1 from the ECX register. And then once you've done that, then you check and you ask the question, hey, are you 0 yet? And if the answer is yes, the answer is I am 0, you fall through and the loop completes. But on the other hand, if it's not 0, you jump and you go back to the label. So like if, so here is an example. Oops, I guess there's not an example just yet, but here's more information about it. But in this case, like something like this, let's take a look here. So if I have the ECX register, you got to make sure it's the ECX register. If you accidentally do CX and you didn't clear out the high portion, your loop is not going to work like you expect. So you have to do the ECX register for this. But what is this code doing? I have AX registers holding 0, ECX is holding 5, and what do I do here is I take, okay, cool, take whatever's in CX, this is fine. The ECX register is holding a bunch of zeros in the extended portion, but the portion that matters is holding the 5. So 5 gets added into AX, and then I say loop again. 5 is decremented to 4, and we loop again. And now we add 4 into whatever's previous. So now 5 plus 4 is 9. I loop again, add the 3, add the 2, add the 1, and I come down. And so at this moment in time, I add 1 into here to get me to 15, and I fall through, and the first thing that happens is I decrement ECX. ECX is now 0. I'm done. The loop completes. So the ECX register has been, I like to call like cannibalized. It's 0. It's been completely reduced, all of its, everything, it's been completely changed to 0, and the AX register holds the correct value. So again, the key here is to remember this all happens before the start of the loop. Or I guess, or two things. Make sure you understand that, yeah, you do all your initializations before the start of the loop. That's what that is saying. But again, remember that when you hit the loop, the first thing that happens is the decrementing of the ECX register. Okay, so what is really happening here is that the instruction pointer is being manipulated, right? Because the next line of code is being manipulated. So the decremented ECX register value must not be 0, blah, 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 blah. So what happens is, again, since this label gives me a memory address for the next line of code, the assembler actually just goes ahead and just figures out from where the instruction pointer is now, what would it subtract off to get back to the next line of code that's right under the label? And it basically adds that in, or if you want to think of it, subtracts that in, so it goes back to where it needs to come from. And this is called a relative offset. And in 32-bit processing, you can only loop and you can only do these comparisons and jumps with an 8-bit integer value. And it says, which means, and what that means is, I'm only allowed to move, since it's a signed integer value, because I can jump forward and backwards. I can say I can only move 128 bytes into the past and 127 bytes into the future. And that sounds like, maybe it sounds like a lot, maybe it doesn't, but what that realistically means is you can only move maybe 20 or 30 lines backwards or forwards because of how many bytes every line of code is. And there's no standard because every line of code needs a different number of bytes to be represented correctly. So occasionally, especially on finals and stuff like that, when students just copy paste code with if statements and sort of thing, that's when you'll see that error, when it's just too far. You can't, because it's an 8-bit quantity, it can't go back to where you want to because it's just too far using an 8-bit value for that subtraction. Okay, so here, coming back to this idea, let's talk about, just to continue this, let's talk about what we see, because it's pretty cool, all the nerdy little cool stuff here. Okay, so what you see is the actual assembly code, and what you see here is just a representation of the machine code. I don't know if it's 100% correct, but the stuff that matters is here. So here is the offset of our code, 0, 4, 9, C. But again, notice this is all hex. So this is 1 byte, 2 byte, 3 byte, 4 bytes. This is 5 bytes of storage for this. This is 3 bytes, and this is 2 bytes. So you can see again, every loop, or say every operation has a different number bytes of code to represent it. But the key here is what we're going to do. What you see, E2FB, and what that means here, E2 is supposedly is the loop instruction. Okay, we'll go with that. But what happens that what comes after the operand for that is FB, which is -5. And so what happens is when you run a line of code, the instruction pointer automatically increases. So it goes to, in this case, it's going from 0 to 4 to 9 to C as it's doing its work. And when it gets to E, it says, oh, I have to loop again. And what it does is it adds FB to this, and FB is -5. And what is E but 14 in hex? 14 plus -5, or 14 minus 5, brings me back to 9. So whenever this works, it goes, does the line of code, comes here, loops, and then whatever happens when this finally falls through, it doesn't jump back, but it just goes to this line of code, and now whatever would be here is the next line of code that gets run. So I think it's pretty cool. You know, sometimes it's a pure memory address that gets worked out, and sometimes it's an offset. And in 64-bit mode, basically all bets are off now. In 64-bit mode, you can move anywhere you want in code. But we're working in 32-bit mode, so we're restricted a little more than you might want to be. So a couple R turns before we call it a night here. I think that's about all we have left inside of this lecture. So let's see. What will the AX register hold when this loop completes? So we have 6 for the AX register, 4 for the ECX register. So we're just running through the code. And all that stuff I was talking about, the nerdy stuff there about the actual nuts and bolts of what happens, we don't have to really worry about as long as we follow the labels and keep working through this. So I say, okay, increment AX, and then loop again. And remember what the loop does. It increments or decrements and then asks the question, are you 0 yet? And so the answer is obviously no. Comes back around, increments that, decrements that, not 0. Increments this, decrements that, not 0. Increments this, decrements this, 0, done. And so the answer to this problem is AX register will hold 10 when everything is said and done. Okay, so there you go. And so that's correct. And so now this one's a little interesting. So let's put, doesn't matter what, let's just put 5 into the AX register, and I'll put 0 into the ECX register. Hopefully you can see where this one's going. How many times will this loop operate and be executed before we're done? And you're like, 0, of course 0. But I'm like, no, that's not how this works, right? Because this is like a do-while loop. If you want to think of it, you do the code, then you loop again if it needs to be. There's no check up front. So I'm like, okay, let's increment whatever's in AX. Okay, 6 now. And so now here's the fun part. I decrement, because that's what a loop does. It decrements ECX. I'm essentially at -1, whatever that is, right? Is that 0? And the answer is no. But what is that? What is -1 when we're dealing with true binary? That is 4.29 billion something. And so you got to watch out. That's how many times the loop will operate. 4,294,967,296 times. Because the decrement happens first, and then it'll just keep on going forever. It won't break on us or anything. We'll just get overflows and stuff like that. It will stop. It's just, it's going to take quite a few more times than we need. So you got to watch out for that. So you got to make sure ECX register holds at least a 1, so that it doesn't go continuously forward with something like that. Okay, I guess we have a few more little tiny things. We're just tying everything together, and then we really are calling it a day here. So let's see. This code will sum up the elements of a word array. Let's put it all together here. So this uses everything from all 40 slides of this chapter so far. So I have 4 elements. So the sum of this should be A00 at the end of the day, right? Because 1 plus 2 plus 3 plus 4 is 10. 10 in hex is A. So A00 should be the result. But we're not going to necessarily worry about that. I guess we could. Let's take a look. What will I need? I'll need EDI. Okay, let's just say I'll need EDI. I will need ECX, which I have. I'll need AX. And that's about it. So let me just move that over to the right, bold it up. Hold that up like I have. Okay, so what do we got? Take the offset of A and move it into EDI. And let's just, for the sake of simplicity, let's just say it's just 0. It's memory location address 0. Okay, I thought, whatever, I hate text. I hate when text goes to the left. Anyway, so that's holding the memory address of the first element in this array. Okay, so ECX holds the length of. I can go back and figure out this thing has 4 elements. So I can fill this in with a 4. AX holds a 0. We've initialized everything. That was one of those rules, right? Initialize everything prior to hitting the loop. That's true in assembly language. That's true in any other language you can imagine here. So now let's talk about the rest of the code here. So we'll only go through this 4 times. So we'll say, okay, go to EDI, which is the memory address of the first element here. Okay, dereference it and put it into AX. So the 100 hex would go into the AX register. All right, fair enough. This is all hex, okay? Yeah, it's all hex. So anyway, so now I do, okay, add type A to EDI. Type A, how many bytes is every element of A? 2. Okay, so now memory address of 2. We added 2 to this thing. Loop again, meaning subtract off and go, nope, not 0 yet. Come back around. And now this says go to element number, or 2 bytes over, not element 2, byte 2. Goes over to 200, put it into AX, and notice it's an add here. It's not a move, it's an add. So now this becomes 300 hex. Type A, move this over 2 bytes. Decrement this thing. You guys know how loops work, right? So decrement this thing, not 0 yet. Bear with me for a couple more iterations. Go to EDI, get me 4 bytes over. Joop, joop, joop. Here we go, 300 hex, add it in. 600 goes. Type A, 2 bytes over, move it over. Oops, address of 6. Move this thing down to 1 and say not 0 yet. So now we go one more time here. Go to element 6, or byte 6, 0, 2, 4, 6. Add this in. I get A00. The text again. Details. Type A. Move this thing over. This is what's interesting. This thing is now pointing to byte 8. But it's not going to matter at the end of the day, because when I hit loop again, this decrements, and I'm done. I fall through. There's other things to do. So what do we get out of this? ECX completely reduced down to 0. EDI, instead of pointing to the beginning of the array, is now pointing outside of it over here into who knows what. That could be somewhere I'm not even allowed to touch. The operating system might give me a fit. I don't know. But as long as you don't dereference it, you're totally allowed to have that value stored in there. And then the AX register is generally what we care about, right? Because that's holding the correct value for everything that we're doing here. Okay, so let's see. Don't we see it? Nope. What is going on here? Oh, so let's see. Your turn. Double word versus, okay, so what's the difference here? This was a word array. What's the difference between a word array and a double word array? Not much. Right, just looking at this, you go, okay, the word becomes double word here. And then instead of using AX to hold words, I'm using EAX to hold double words. That's about it. That's it, right? So yeah, this line changed slightly, this line changed slightly, this, and nothing else did. It's just in those 3 places. And it just takes into account the larger data type. Pretty good there? The truly final example of this lecture. Let us try to copy a string. How easy is this in any other language? A equals B, right? Oh, goodness gracious, right? So let's make this work in assembly language. So I have this phrase, so believable, with a null terminated string with a comma 0. Again, I need that for every string, and I have to remember that. I can't forget this, otherwise big problems down the line. So notice now everything here, B byte size of A dupe 0. So cool. What that means is, how many elements are there, right? This number, size of A, is a hard-coded number. So whatever number of bytes, 14, 15, 13, whatever it is, that number dupe 0. And so I believe, if I remember right, I am not going to go ahead and do this in Visual Studio, but I don't believe you have to initialize the values. I think you could leave it uninitialized. But the thought process here is, if I initialize all of those bytes to 0, as I'm filling in, the null terminating character will make its way to the final byte. Because I have to make sure that I copy every byte, including the null terminating character, because if I don't include the null terminating character, when I go to print it out later, it's just going to fly on by and just keep on going. So I have to copy everything along. So let's see, there's 2 different ways to do this. So this is way number 1 here. So let's see, yeah, modify this code. This is to use different indexing modes. So what is this? Again, initialize everything up front and say, okay, ESI is 0. Okay, let me just I won't do the whole thing, but just to say, okay, ESI is 0, literal 0, okay? And ECX holds size of A, which is, let's just say 14. I don't know, I don't care enough to know. I'm not going to do this 14 times over. And so what are we doing here? I'll just do this 2 times and we'll call it a day. So I say, oh, okay, go to A, but give me ESI bytes over from it, right? That's what this is saying. So go to the pointer A and go 0 bytes over. So that basically, and then dereference that, and that's going to get me the capital S. And the capital S will go into the AL register. Okay, it is ASCII S, whatever value that is. And so what I do then, notice this is a 2-step process, and then I take what's in the AL register, which is the capital S, and then in respective order, I put it into the same location, the 0th location inside of the B string. So now the B would have a capital S and a whole bunch of null terminating characters after it. I increment ESI to 1, and I do loop again, and now this becomes 13. It's not 0, so I come back around and I do it again. And so again, this is the last time I'll do this. So now take A, go 1 byte over, and that's the little O, and put that little O into the AL register. Take whatever's in the AL register, which is the little O, move it into the element 1 of the B. So now B holds S and O, and then just continue on. You guys know how loops work. And so I think this is a pretty simple, this is what, 6 lines of code and 1 label to get the job done. And this uses the way that most programmers think of using the array notation. But now on the other hand, if you want to go the other way, oh my goodness, how much more complicated can this be, right? This uses the other index modes where you're relying on the pointers directly. And so run this, go through this if you want to, and just notice how more complicated it is. It's 8 lines of code, still 1 label, more lines of code and just offsets and sizes and types and all sorts of crazy nonsense. It's more complicated than it needs to be to get the same job done. So end result is you might like one way over the other, but if you know how to use both ways, you can use it to your advantage so that whenever you come up with an example that can use one or the other better than the other, you just go to town on it. But if all you know is one way, you can have this where you have much more complicated code. And I see a lot here that could have an error in it. There's a lot everywhere. But this, look at all that, just simple. It looks so simple compared to all these offsets and sizes and all this stuff going on. So that's the end of this discussion. Thank goodness, right? I never know how long the video goes until I put all the pieces together and then my jaw drops. An hour, hour 10, whatever this is going to be. So, as always, any questions, swardb@cod.edu is my email address. Let me know if I screwed up something. I mean, I'm talking a lot. I'm thinking a lot. This is a completely different atmosphere than standing in front of students. And, this is still new to me. Even though I made hours and hours of content, still all new to me. So, swardb@cod.edu. Send me a comment here on YouTube. Get a hold of me somehow. Again, never let your questions sit. Everything snowballs. And if you don't want snowballs in this class, you want to make sure that you understand every topic as we go through. So thanks for sticking through this video. And, I'm making the next video next year, so we'll see you next time. Thanks for sticking along.